Okay, now I want to work another example and actually have multiple elements rather than just a single spring element. So we'll work the problems that we worked just now, but with two spring elements. And to make it simple, so what I'm going to have as a model or as a system is I'm going to have a spring, a single spring, connected with another spring in. These are 1D elements, so there's only one way to connect them. I'm going to have my x1 like I had before. So this is node 1, node 2, and node 3. This then will be x2, and this will be x3. Now, what I'm going to do, I'm not going to have any kind of external force on node 2, but I am going to put or have a force on F1 and then other force on F or on 3. So we'll have reaction forces at the ends of the two springs. As we saw before with the single element, whether you have the springs in tension or compression, really you get the same expression. So that relationship that we worked out is valid for whether these springs are in tension or compression. Let's work the first problem that we had before. So we will give our nodal displacements, and x1 will be 0.2 meters. These are the same k's that we had before. X3, not x2, x3 will be 0.1 meters. Okay, so actually what you can see is that this system, they're going to be in it's going to be in compression because the left hand node moves further to the right than the right node does. And then what's unknown here is we don't know what F1 is, and we don't know what F3 is. The other thing that we don't know is we don't know what the nodal displacement is at 2. It's given at x1 and x3, but we need to figure out what it's going to be at x2. Now we're going to continue and have what we had before. We'll just have k equals to 1,000 like we did before, newtons per meter. Okay. And so we're trying to find out the things that we don't know, the reactions at the end, and then the movement, the nodal displacement of x2. So our element stiffness matrices are the same as they were before. Well, I'll write it for the first element, and we're going to have our 1,000 here, minus 1,000 here, 1,000 here, minus 1,000 here. And we know our nodal, no, sorry about this. This is the first element, and we do not know what the nodal displacement of x2 is. But what we do know is we do know that x1 is 0.2, and that's meters, and we don't know what x2 is. So that's our first element. Our second element, F2 and F3, the nodes are node 2 and node 3. Well, the element stiffness matrix is the same. The second spring is the same as the first spring. I specified that. Doesn't need to be, but in this case it is because we want to see what happens. And then we do not know x2, and we do know x3. Okay, so these are the local element stiffness relationships for element 1, and the way I like to do elements is put a number there and a square around it rather than a circle, and this is element 2. Okay. Now what we need to do is we need to assemble these into a global stiffness matrix rather than two single local stiffness matrices. So we need to add these in correctly. And so our global matrix, or global stiffness equation, I guess you could say, is, well, now we have three nodes, and therefore our system is going to be a 3 by 3, not a 2 by 3. And the way that you add these together, well, first of all, we just come out here and label our forces F1, F2, F3, okay? And then we need to make our global stiffness matrix, and the way that you do that is you put this matrix in where it belongs, and that's in the upper left, because over here on the right, let's see, let me leave myself some space here, we're going to have x1, x2, and x3, so we're going to have 0.2, this is x2, which is unknown, and then we'll have 0.1, which is x3. So we add our local element matrices into the global stiffness matrix, and what you can see is we're going to make a 3 by 3 out of this, but the F1, F2, and 0.2 and x2, which is what this is, it goes in the upper left, minus 1,000, minus 1,000. Now I have to be careful here because this element here, the second element, the upper left-hand corner of it overlaps with upper left-hand, lower right-hand corner of the first local stiffness matrix. So what you do is you add those together. These are added into the global stiffness matrix. So I will have 1,000 there, which is the sum of that number and that number. And then down here below, I continue with my local matrix. And this will be 1,000 right here. And I'll have a 0 in here and a 0 in here because, well, there's nothing there when you add these into the global stiffness matrix. There's nothing that fills these places up. So anyway, now we have three equations, and we can start to solve them. One thing that I do know, we actually have three unknowns, and I haven't indicated that here, and I should. We don't have any external forces at node 2, so this here is going to be 0. Okay? Now, actually, what we can see, we've got a number of things that we can find. We do x2, and in the second equation, if we use the second equation in here, what we can see is we'll have a 0 over here on the left equals, and then it's minus 1,000 times a 0.2. We'll check our units in a minute. And then plus 2,000 times x2, and then plus 1,000, no, sorry, minus 1,000. It's this times that, so it's minus 1,000 times 0.1. Okay, let me get us some space here. Now what we can do, as you can see, is we have these negatives here, and we can move them over to the left-hand side. Let's just see what these are here. We can just, go ahead and calculate them. So this is going to be minus 200, and this is newtons per meter times meters, so this is going to be newtons. Then we have this, and then over here on the right, we're going to have minus 1,000 times 0.1. It's going to be minus 100. And it's newtons per meter times meter, so it's going to be newtons also. So then we add these two together, and we get 300. We can move it over to the left-hand side. So we have 300 equals 2,000 times x2. so we can solve for x2. Get some space here. x2 is equal to 300, and this is going to be newtons divided by, I'll get a little more space here, 2,000 newtons per meter. Okay, so if we perform this calculation, we can do it by hand really. 3 divided by 2 would be 1.5, but it's 3 divided by 20, so it's going to be 0.15 meters. Okay, to the right, because it's positive. Now, if we go back up and look at our original problem, we know that this moves 0.2 to the right, this moves 0.1 to the right, and now what we're finding out, if we have equal springs here, we're finding out that this moves an average of what this moves and what this moves. So this moves 0.2, this moves 0.1, and this moves 0.15, and that makes sense. Okay, so our system delivered that to us. And now we still have to calculate our nodal forces, but what I'm going to do is I'm going to stop here and start a new video because we're already at 11 minutes.